Welcome to Part 5 topic Automating Infrastructure and Applications Security in Modern Cloud Environments. Security can no longer be treated as a final checkpoint that happens just before deployment. Infrastructure and applications change constantly. New code is pushed, new services are created, and configurations evolve every day. If security relies on manual reviews and after-the-fact fixes, it will always lag behind the pace of development. That is why automating infrastructure and application security is no longer optional. It is a core requirement for operating securely at scale. Automation shifts security from a reactive discipline to a proactive one. Instead of waiting for vulnerabilities to be discovered in production, security controls are embedded directly into the systems that build, test, and deploy applications. This approach aligns closely with modern DevOps practices, where infrastructure is defined as code and deployments are driven by pipelines rather than human intervention. At the heart of this approach is the idea of integrating security into the continuous integration and continuous delivery process. Every time developers commit code or build an artifact, automated security checks run alongside functional tests. These checks look for known vulnerabilities, insecure configurations, and policy violations long before the application ever reaches a live environment. One of the most important areas to automate is vulnerability scanning. Most security breaches do not rely on unknown, exotic attacks. They exploit well-documented weaknesses known as common vulnerabilities and exposures, or CVEs. These vulnerabilities exist in operating systems, libraries, and application dependencies. When scanning is automated, container images, virtual machine images, and application components are continuously inspected for these known issues. In a cloud-native setup, this scanning happens at multiple stages. Container images can be scanned as soon as they are built, before they are stored in a registry. Running workloads can also be scanned to detect vulnerabilities introduced through updates or configuration drift. This layered approach ensures that security issues are caught early and monitored continuously. Automation also enables a concept often referred to as shifting security left. Instead of security being the responsibility of a separate team at the end of the process, developers receive feedback early, when changes are easier and cheaper to fix. A failed security check in a pipeline stops a risky deployment before it becomes an incident. Over time, this creates safer development habits and more resilient systems. Another critical aspect of automating infrastructure and application security is enforcing trust in what gets deployed. Not every build artifact should be allowed to run in production. Automated policies can ensure that only verified and approved images are deployed. This prevents unauthorized or tampered components from entering sensitive environments. In practical terms, this means cryptographically verifying artifacts and enforcing deployment rules automatically. An image that has not passed required security checks, or that has not been explicitly approved, is simply blocked. No human intervention is needed, and no exceptions are quietly introduced under pressure. Automation also plays a major role in maintaining secure infrastructure over time. Virtual machine images and container base images must be updated regularly with security patches. By automating image creation and maintenance, organizations ensure that new workloads always start from a hardened and up-to-date baseline. This reduces the risk of long-lived vulnerabilities hiding in older systems. Just as important is the ability to detect when systems drift away from their intended configuration. Policies defined as code can be continuously evaluated against the actual state of the environment. If a firewall rule changes unexpectedly, or if a resource violates a security standard, automated detection highlights the issue immediately. This allows teams to respond quickly, often automatically, before the problem escalates. Ultimately, automating infrastructure and application security is about consistency, speed, and scale. Humans are not good at repeating complex security checks thousands of times without error. Machines are. By encoding security knowledge into pipelines, policies, and automated scanners, organizations build defenses that operate continuously and reliably. The result is a security posture that grows stronger as systems scale, not weaker. Instead of slowing innovation, security becomes an enabler. Applications move faster, infrastructure becomes more predictable, and risks are identified and controlled before they turn into incidents. This is the true goal of automating infrastructure and application security, building systems that are secure by design, secure by default, and secure at every stage of their life cycle. Automating security, scanning for CVEs via SIS/SEED in modern cloud environments. Security can no longer be a manual, occasional activity. Applications change rapidly, new code is deployed multiple times a day, and dependencies are constantly updated. In this fast-moving world, vulnerabilities can appear silently, hidden inside container images, open-source libraries, or operating system packages. This is why automating security scanning for known vulnerabilities, commonly called CVEs, becomes a critical part of both infrastructure and application security. A CVE, or Common Vulnerabilities and Exposures Entry, is a publicly documented security flaw. Each CVE represents a known weakness that attackers already understand and actively exploit. If these vulnerabilities are allowed to slip into production systems, they create open doors for compromise. The goal of automated security scanning is simple but powerful. Detect these weaknesses early, ideally before the application ever reaches a live environment. The most effective place to perform this scanning is inside the CI/CD pipeline. The pipeline already represents the journey your code takes, from a developer's laptop to a running service in production. By embedding security checks directly into this journey, security becomes a built-in process rather than an afterthought. As code is committed to a repository, the CI system begins its work. Alongside compiling code and running tests, automated scanners analyze the application and its dependencies. For container-based workloads, this often includes scanning container images for vulnerable operating system packages and libraries. For application code, scanners inspect dependency files to identify insecure versions of frameworks or third-party modules. These tools compare what they find against constantly updated vulnerability databases. When a match is detected, the pipeline is immediately aware. Instead of discovering the problem weeks later during a security audit, the issue is surfaced within minutes, while the code is still fresh in the developer's mind. One of the key advantages of automating CVE scanning is consistency. Every build is scanned the same way, using the same rules, without relying on human memory or judgment. This eliminates gaps that often appear when security checks are performed manually or only at specific milestones. Automation also enables clear enforcement. Organizations can define policies that determine what happens when vulnerabilities are found. For example, low-severity issues might generate warnings, while high or critical vulnerabilities can automatically fail the build. In this way, insecure artifacts are prevented from moving forward in the deployment process. Security becomes a gate, not a suggestion. Another important benefit is visibility. Automated scans produce detailed reports that show exactly where vulnerabilities exist, how severe they are, and often how to fix them. Over time, these reports help teams identify patterns, such as repeatedly vulnerable libraries or risky base images, allowing them to improve their overall security posture. In cloud-native environments, this automation integrates naturally with managed services. Container registries can continuously scan stored images, CI systems can trigger scans on every commit, and deployment platforms can block workloads that do not meet security standards. Together, these controls form a continuous security feedback loop that operates at machine speed. Ultimately, automating security scanning for CVEs through CI/CD pipelines shifts security left. Problems are detected early, fixes are cheaper and faster, and production environments remain cleaner and more resilient. Instead of reacting to breaches, teams proactively reduce risk with every line of code they deploy. This is not just automation for convenience. It is automation as a foundational layer of modern cloud security. Configuring binary authorization for GKE or cloud run-in modern cloud environments. Security cannot depend on manual checks or human judgment alone. As systems grow larger and deployments become more frequent, every step of the delivery pipeline must be able to protect itself automatically. This is where automating infrastructure and application security becomes essential, And one of the most powerful tools for this purpose is binary authorization. To understand binary authorization, imagine a checkpoint placed just before your application is allowed to run. Even if a container image is successfully built, stored, and referenced by a deployment, it is not automatically trusted. Instead, it must prove that it meets your organization's security rules. Binary authorization is that checkpoint. It decides whether an application is allowed to run based on verifiable evidence, not assumptions. In Google Kubernetes Engine and Cloud Run, applications are commonly deployed as container images. These images often pass through multiple systems such as build pipelines, artifact registries, and deployment tools. At each step, there is a risk that an image could be modified, replaced, or built without proper security checks. Binary authorization reduces this risk by enforcing a policy that only approved images are allowed to run. The approval process is based on cryptographic attestations. An attestation is a signed statement that confirms something important about an image. For example, it can confirm that the image was built by a trusted pipeline, that it passed vulnerability scanning, or that it was reviewed and approved by a security team. These attestations are signed using trusted keys, which means they cannot be forged or altered without detection. When binary authorization is enabled, GKE or Cloud Run checks these attestations at deployment time. If the image does not have the required attestations, the deployment is blocked. The application never starts. This ensures that security controls are enforced automatically and consistently, no matter how fast your teams deploy. In a typical setup, the process begins in the build stage. A continuous integration system builds the container image and runs security checks, such as vulnerability scans and policy validations. If the image passes these checks, the system creates an attestation and signs it using a trusted key. The image and its attestation are then stored securely. Later, when a deployment is attempted, binary authorization evaluates the image against the defined policy. The policy specifies which attestations are required and which signing authorities are trusted. If everything matches, the deployment proceeds. If not, it fails immediately. This creates a strong link between your security processes and your runtime environment. For GKE, binary authorization acts as a gatekeeper for pods. Even if someone has permission to deploy workloads to the cluster, they cannot bypass the authorization policy. This helps protect against insider threats, misconfigurations, and compromised credentials. It also ensures that test images or unverified builds never reach production. For Cloud Run, the same principle applies in a serverless environment. Although Cloud Run abstracts away infrastructure management, binary authorization still enforces image trust. This means you can enjoy the speed and simplicity of serverless deployments without sacrificing control over what code is allowed to run. One of the key benefits of binary authorization is that it shifts security left while still enforcing it at the last possible moment. Developers can move quickly, but the platform remains protected. Security teams define the rules once, and those rules are applied automatically every time an application is deployed. Over time, this approach builds confidence. You know that every running workload has passed through approved processes. You know that accidental deployments, malicious images, or unreviewed changes are stopped before they can cause damage. This is automation not just for convenience, but for trust. By configuring binary authorization for GKE or Cloud Run, you turn security into a built-in feature of your delivery pipeline. Instead of relying on hope or manual checks, you rely on verified proof. In a world of rapid deployments and constant change, that proof makes all the difference. Automating VM image creation, hardening, patch management in modern cloud environments. Security cannot rely on manual effort alone. Infrastructure changes frequently, applications are updated continuously, and threats evolve every day. To keep up with this pace, security must be automated and embedded directly into how infrastructure and applications are built and maintained. Automating infrastructure and application security means turning security best practices into repeatable, reliable processes that run consistently without depending on human memory or manual intervention. One of the most important areas where automation plays a critical role is virtual machine image creation. A virtual machine image is the starting point for every VM you launch. If that image is weak, outdated, or misconfigured, every VM created from it inherits those weaknesses. Automating VM image creation ensures that every instance starts from a secure and standardized foundation. Instead of manually creating VM images, organizations use automated image pipelines. These pipelines build images in a controlled environment using predefined templates and scripts. During the build process, the operating system is installed with secure defaults, unnecessary services are removed, and only required packages are included. This reduces the attack surface from the very beginning. By automating this process, you eliminate inconsistencies that often arise when images are created by hand. Hardening is a key part of automated image creation. Hardening means tightening the system configuration to reduce vulnerabilities. This includes disabling unused ports, enforcing strong authentication settings, applying secure file permissions, and configuring logging and monitoring agents. When hardening is automated, every VM image is built with the same security posture. There is no risk that one system is accidentally left more open than another. Automation also allows security teams to codify compliance requirements directly into the image build process. For example, password policies, audit logging settings, and encryption configurations can be enforced automatically. If an image does not meet these requirements, the build fails. This ensures that only compliant images are approved for use, long before they reach production. Once secure images are created, the next challenge is keeping systems up to date. This is where automated patch management becomes essential. Operating systems and software regularly receive updates that fix vulnerabilities. If patches are delayed or forgotten, attackers often exploit these known weaknesses. Manual patching is slow, error-prone, and difficult to scale, especially in large environments. Automated patch management solves this by regularly scanning systems for missing updates and applying patches according to predefined schedules and policies. Updates can be tested in staging environments before being rolled out broadly, reducing the risk of breaking applications. Critical security patches can be prioritized and applied faster, shrinking the window of exposure. Automation also helps manage patching across different environments. Development, testing, and production systems can follow separate patching strategies while still being centrally controlled. Systems that cannot be patched immediately can be flagged, monitored, and isolated if necessary, ensuring visibility into risk rather than leaving blind spots. Another important aspect of automated patch management is image-based patching. Instead of patching running systems repeatedly, organizations rebuild VM images with the latest updates and redeploy them. Old instances are replaced with new ones based on updated images. This approach reduces configuration drift and ensures that systems remain consistent over time. When image creation, hardening, and patch management are automated together, security becomes part of the lifecycle rather than an afterthought. Every new VM starts secure. Every update follows policy. Every change is repeatable and auditable. This reduces human error, improves response time to vulnerabilities, and strengthens the overall security posture of the cloud environment. In essence, automating VM image creation, hardening, and patch management transforms security from a reactive task into a proactive system. It ensures that security scales with infrastructure, keeps pace with change, and remains consistent no matter how large or complex the environment becomes. Automating container image hardening and maintenance. Modern cloud environments move fast. Applications are built, updated, and deployed many times a day. Containers make this speed possible, but they also introduce a new security challenge. Every container image is a bundle of code, libraries, and system components. If even one of those pieces is vulnerable, that weakness can be carried into production automatically and at scale. That is why automating container image hardening and maintenance is so critical. Container image hardening begins with the idea that images should be as small and simple as possible. Every extra package, tool, or library increases the attack surface. In practice, this means starting from minimal base images that include only what the application truly needs to run. Development tools, debuggers, and unused system utilities should never be present in production images. Automation helps enforce this consistently, so teams do not rely on memory or manual reviews. Another key part of hardening is ensuring that containers do not run with unnecessary privileges. Automated build pipelines can enforce rules such as running processes as non-root users, disabling privilege escalation, and locking down file system access. When these rules are built into the image creation process, insecure configurations are blocked before the image is ever published. Vulnerability scanning is a central pillar of automated container security. Each time an image is built, automated scanners analyze the operating system packages and application dependencies inside the image. These scanners compare components against known vulnerability databases. If critical or high-risk vulnerabilities are found, the pipeline can fail automatically. This prevents insecure images from moving forward into testing or production environments. Hardening does not stop at the first scan. Vulnerabilities are discovered constantly, even in images that were secure yesterday. Automated maintenance ensures that container images stay secure over time. This usually involves regularly rebuilding images with updated base layers and patch dependencies. Instead of patching running containers, which breaks the container model, new images are built and redeployed. Automation makes this process repeatable and reliable. Image signing and verification add another layer of protection. Automated systems can sign container images after they pass security checks. At deployment time, platforms verify these signatures and reject images that have been tampered with or come from untrusted sources. This ensures that only approved, hardened images are allowed to run in production. Automation also plays a role in enforcing consistency across teams. Security policies such as approved base images, mandatory scans, and minimum security standards can be encoded directly into build pipelines. This removes guesswork and reduces human error. Every team follows the same rules, and every image is evaluated the same way. In mature environments, automated container image hardening becomes part of a continuous feedback loop. Build systems detect vulnerabilities, security teams refine policies, and developers receive fast feedback when something is wrong. Over time, this creates a culture where security is not an afterthought, but an automatic outcome of the development process. By automating container image hardening and maintenance, organizations reduce risk without slowing down innovation. Security checks run silently in the background, images stay up to date, and vulnerabilities are caught early. The result is a container ecosystem that is not only fast and scalable, but also resilient and secure by design. Managing policy and drift detection at scale. When cloud environments are small, policies are often managed by hand. An administrator reviews settings, applies rules, and periodically checks whether systems still look the way they should. But as environments grow to hundreds or thousands of projects, services, and resources, this approach quickly breaks down. At scale, security policies must be automated, continuously enforced, and constantly verified. This is where managing policy and drift detection becomes essential. A policy represents how your cloud environment is supposed to look and behave. It defines what is allowed, what is denied, and what must always remain true. Examples include rules about where resources can be created, whether encryption is mandatory, or whether public access is allowed. Once a policy is defined, the goal is simple. The environment should never drift away from it. Drift happens when the real configuration of resources slowly diverges from the intended state. A developer may temporarily open access for testing and forget to close it. An automated deployment might override a secure setting. A legacy system may not comply with newer security standards. Over time, these small changes accumulate, creating gaps that attackers can exploit. To manage this at scale, policies must be expressed as code rather than human instructions. Policy as code allows organizations to define security requirements in a consistent, machine-readable way. These definitions can be version-controlled, reviewed, tested, and deployed just like application code. This removes ambiguity and ensures that every environment follows the same rules. Once policies are defined, they must be enforced automatically. Enforcement ensures that non-compliant configurations are either blocked immediately or flagged as violations. For example, if a policy states that all storage must be encrypted, any attempt to create an unencrypted resource is denied at creation time. This prevents misconfigurations before they ever reach production. However, enforcement alone is not enough. Cloud environments are dynamic, and configurations can change after resources are created. This is why continuous drift detection is critical. Drift detection constantly compares the current state of the environment against the expected policy state. When a difference is detected, it generates a finding that highlights what changed and why it matters. At scale, this detection must operate across organizations, folders, and projects simultaneously. Manual reviews are impossible, so automated scanners continuously evaluate resources in near real time or through scheduled scans. When drift is found, teams are alerted with clear, actionable information rather than raw configuration data. In advanced setups, detection is paired with automated remediation. Instead of only reporting a violation, the system can automatically fix it. If a resource becomes publicly accessible against policy, access can be revoked immediately. If encryption is disabled, it can be re-enabled without human intervention. This approach is often referred to as self-healing security. Custom policies and detectors play a key role here. Every organization has unique requirements that go beyond default security checks. By defining custom rules, teams can detect misconfigurations that are specific to their architecture, compliance obligations, or risk tolerance. These custom rules become part of the same automated pipeline, operating alongside built-in security controls. At its core, managing policy and drift detection at scale is about consistency and resilience. It ensures that security intent is clearly defined, automatically enforced, continuously monitored, and rapidly corrected. Instead of reacting to incidents after damage is done, organizations maintain a steady, controlled security posture, even as their cloud environments evolve and grow. In modern cloud security operations, this shift from manual oversight to automated governance is not optional. It is the only practical way to maintain trust, control, and visibility at scale. Configuring logging, monitoring, and detection in modern cloud environments. Security does not end with access control or network boundaries. It continues every second your systems are running. This is where logging, monitoring, and detection become critical. They give your security team visibility, evidence, and the ability to respond when something goes wrong. Logging is the foundation. In Google Cloud, almost every action leaves a trace. Every API call, configuration change, network connection, and system event can be recorded. These records answer the most important security questions: who did what, where it happened, and when it occurred. Without logs, incidents become guesses. With logs, they become investigations backed by facts. Cloud logging is the central place where these records are collected. It stores logs generated by Google Cloud Services, by Google-provided components such as GKE, and by your own applications. Among all log types, security logs are the most valuable. Cloud audit logs track administrative actions and data access, showing when resources are created, modified, or accessed. These logs are essential for accountability, compliance, and non-repudiation, meaning actions cannot be denied later. Not all logs are enabled by default. Some, especially data access audit logs, can generate large volumes of data and increase costs. This means logging must be intentional. You decide which services, projects, or identities should have deeper visibility. A good logging strategy balances security needs with cost control, ensuring that high-risk actions are always captured while unnecessary noise is reduced. Network visibility is another critical piece. Firewall rules logging shows which traffic is allowed or denied by your firewall policies. VPC flow logs go deeper by capturing samples of network flows, entering and leaving virtual machines. These logs help detect suspicious traffic patterns, investigate breaches, and even optimize network costs. Because flow logs can grow quickly, sampling rates and aggregation intervals must be chosen carefully to avoid unexpected charges. Logs become even more powerful when they are centralized. Instead of storing logs separately in every project, organizations often aggregate them into dedicated log buckets. This creates a single source of truth for investigations and audits. Centralization also simplifies long-term retention, encryption, and access control. Retention policies define how long logs are kept, from days to years, depending on regulatory and operational requirements. Access to logs must be tightly controlled. Logs often contain sensitive information, and too many readers increase the attack surface. A clear access model ensures that only the right people can view, analyze, or manage logs. Encryption adds another layer of protection. While logs are encrypted by default, some organizations require customer-managed encryption keys to maintain full control over how log data is protected. Logging alone is not enough. Monitoring turns raw data into signals. Cloud monitoring works alongside cloud logging to detect abnormal behavior, trigger alerts, and support incident response. Metrics derived from logs can show spikes in failed logins, unusual network activity, or sudden configuration changes. These signals allow teams to act before an issue becomes a major incident. Detection takes this one step further. Security Command Center continuously analyzes logs and resources to identify vulnerabilities, misconfigurations, and active threats. Built-in services such as security health analytics and event threat detection scan your environment and produce findings when risks are detected. These findings point directly to affected resources and explain what went wrong and why it matters. Advanced organizations go beyond built-in detections by creating custom detection rules. These rules reflect your specific security policies and business risks. Some detections can even trigger automatic remediation, fixing issues as soon as they are discovered. This moves security from a reactive process to a proactive, and in some cases, self-healing system. Together, logging, monitoring, and detection form the nervous system of your cloud security operations. Logging provides evidence, monitoring provides awareness, and detection provides intelligence. When designed correctly, these systems ensure that no critical action goes unnoticed, no major threat goes undetected, and every incident can be investigated with confidence. Topic: understanding cloud logging. Before we talk about monitoring alerts or detecting threats, it is important to understand the foundation that makes all of that possible. That foundation is cloud logging. Cloud logging is the central nervous system of visibility in Google Cloud. Every action, every event, and every signal that matters for security or operations eventually passes through it. Without logging, you are effectively blind. You may have strong security controls in place, but if something goes wrong, you will have no evidence, no timeline, and no way to prove what actually happened. Cloud logging is a fully managed service designed to collect, store, search, and route logs from many different sources. These sources include Google Cloud Services, applications running on virtual machines, containers in Kubernetes, serverless workloads, and even systems running outside Google Cloud, such as on-premises infrastructure or other cloud providers. From a security operations point of view, this means cloud logging becomes a single, trusted place where activity across your entire environment can be observed and analyzed. At its core, cloud logging does three fundamental things. First, it receives log entries generated by services and applications. Second, it stores those logs in managed storage. Third, it allows you to search, filter, and route those logs to other systems for deeper analysis or long-term retention. When you create a Google Cloud project, logging is enabled automatically. You do not need to install agents or configure anything to start receiving most platform logs. As soon as you create or modify resources, logs are generated and stored for you. These logs are placed into managed containers called log buckets. Every project starts with two special log buckets. One is called the default bucket, and the other is called the required bucket. The default bucket stores the majority of logs generated by your workloads and services. The required bucket is created and managed by Google and is used to store critical logs that cannot be disabled, such as certain audit logs. This ensures that important security and compliance evidence is always preserved. Each log bucket has a defined retention period. Retention determines how long logs are kept before they are automatically deleted. Some buckets retain logs for a short time, while others retain them for much longer. This balance is important. Short retention reduces storage costs, but long retention is often required for security investigations, audits, or compliance regulations. Once a log reaches the end of its retention period, it is permanently deleted and cannot be recovered. Cloud logging does not only store logs, it also provides powerful tools to explore and analyze them. The Logs Explorer interface allows you to search through massive volumes of log data using structured filters. You can narrow results by resource type, service name, severity level, time range, or even specific fields inside the log payload. This makes it possible to reconstruct events, trace suspicious behavior, or understand how a system behaved at a particular moment in time. In addition to human-driven investigation, cloud logging supports automation. Logs can be accessed programmatically through APIs, which allows security tools, monitoring systems, and incident response workflows to consume logging data automatically. This is critical for detecting threats at scale, where manual inspection is no longer feasible. Another key capability of cloud logging is log routing. Not all logs need to stay in the same place. Some logs may need to be archived for years, some may need to be analyzed using big data tools, and others may need to be streamed in near real time to external security systems. Cloud logging allows you to define rules, called syncs, that route logs to destinations such as BigQuery, cloud storage, PubSub, or even other log buckets in different projects. This makes centralized logging and separation of duties possible. Logs in cloud logging fall into different categories. Some logs are generated by Google Cloud Services themselves, such as network activity, resource changes, or authentication events. Other logs come from software components like Kubernetes system services. Application logs are generated by your own code and help explain what your application is doing internally. Audit logs are especially important for security because they record who did what, when they did it, and which resource was affected. From a security perspective, cloud logging plays a critical role in accountability and non-repudiation. If an incident occurs, logs become evidence. They allow you to prove that an action took place and identify the identity behind it. This is essential not only for incident response, but also for audits, compliance reviews, and trust in automated systems. Cloud logging does not operate in isolation. It works closely with cloud monitoring, which uses logs and metrics to trigger alerts, build dashboards, and surface anomalies. Together, they form the backbone of Google Cloud's observability and security operations capabilities. In simple terms, cloud logging answers one fundamental question: what is happening in your environment right now and in the past? Everything else in logging, monitoring, and detection builds on that answer. Without a clear understanding of cloud logging, effective security monitoring is impossible. Configuring and analyzing network logs. When we talk about configuring and analyzing network logs, we are really talking about visibility. In any cloud environment, data is constantly moving from one place to another. It flows between virtual machines, between services, between on-premises systems and the cloud, and out to the internet. Every one of those movements is a potential security signal. Network logs are how we observe that movement and understand whether the network is behaving the way we expect. Even when strong protections like encryption, firewall rules, and service perimeters are in place, security teams still need proof. They need to confirm that authorized traffic is allowed, unauthorized traffic is blocked, and unexpected behavior is detected early. Network logs provide that evidence. They help answer simple but critical questions: who connected to what, from where, when it happened, and whether it was allowed or denied. One of the first and most important sources of network visibility is firewall rules logging. Firewall rules define what traffic is permitted or denied in a VPC network. When logging is enabled on these rules, every connection attempt that matches the rule can generate a log entry. These logs show whether traffic was allowed or blocked, which rule was applied, and key details about the source and destination of the connection. Over time, this builds a clear picture of how your perimeter defenses are actually being used. Firewall logs are written to cloud logging in the project that owns the network. This detail becomes especially important in shared VPC environments. Even though virtual machines may live in service projects, the firewall rules and their logs belong to the host project. Understanding where these logs are stored is essential when you are investigating incidents or building centralized logging strategies. Once firewall logs are flowing, the next step is analysis. In cloud logging, you can filter logs to focus on exactly what matters. You might look at all firewall activity across a network, narrow it down to a specific subnet, or isolate traffic related to a single virtual machine. You can even analyze connections based on geographic origin to identify traffic coming from unexpected countries. This ability to slice and filter network data turns raw logs into actionable security insights. Firewall logs, however, only tell part of the story. They show how traffic interacts with firewall rules, but they do not capture the full behavior of network flows. This is where VPC flow logs come in. VPC flow logs record samples of network traffic that flows to and from virtual machines. These samples include details about protocols such as TCP, UDP, and ICMP, as well as information about source and destination addresses, ports, and connection outcomes. VPC flow logs are enabled at the subnet level, not on individual virtual machines. When they are turned on, they apply to all virtual machines in that subnet. This design ensures consistent visibility, but also means careful planning is required. Enabling flow logs generates additional data, and that data can increase logging costs if sampling and aggregation settings are not tuned properly. Each flow log represents a summary of traffic observed over a specific time window. You can control how frequently these summaries are generated and how much traffic is sampled. Shorter aggregation intervals and higher sampling rates provide more detailed visibility, but they also increase log volume. Longer intervals and lower sampling reduce costs but may miss fine-grained details. Finding the right balance depends on whether your priority is deep forensic analysis, ongoing monitoring, or cost optimization. Like firewall logs, VPC flow logs are stored in cloud logging and can be queried using the logging query language. You can view flow logs for all subnets in a project, focus on a single subnet, or investigate traffic related to a specific workload. Over time, these logs help establish a baseline of normal network behavior. Once that baseline is understood, deviations become much easier to detect. Together, firewall rules logging and VPC flow logs form the foundation of network visibility in Google Cloud. Firewall logs show how policy decisions are enforced at the perimeter. Flow logs show how traffic actually moves through the network. When analyzed together, they allow security teams to validate controls, investigate suspicious activity, and respond confidently to incidents. Configuring and analyzing network logs is not a one-time task. It is an ongoing process of observation, adjustment, and refinement. As architectures evolve and workloads change, logging configurations must evolve as well. When done correctly, network logs become more than just records of activity. They become a reliable source of truth, supporting detection, investigation, and trust in the security of your cloud environment. Topic: Designing an effective logging strategy. Designing an effective logging strategy starts with a simple but critical question. Why are you collecting logs in the first place? Logging is not just about storing data. It is about creating reliable evidence that explains what happened in your environment, who was involved, where it occurred, and when it took place. A well-designed logging strategy supports security monitoring, incident response, troubleshooting, compliance, and accountability, all at the same time. The first step is to clearly define the purpose and objectives of logging. Some organizations focus primarily on detecting security incidents. Others care more about system reliability, performance analysis, or regulatory compliance. In reality, most environments need to support all of these goals. By being clear about your objectives early, you avoid collecting unnecessary data and ensure that the logs you keep are actually useful when something goes wrong. Once the objectives are clear, the next step is to understand the types of logs and where they come from. In Google Cloud, logs can originate from many sources, such as applications, virtual machines, containers, managed services, networks, and identity systems. There are system logs that describe how infrastructure behaves, application logs that capture business logic and errors, and security and audit logs that record access and configuration changes. Each of these log types serves a different purpose, and not all of them need to be treated the same way. At this stage, it is important to think about your overall logging architecture. Some organizations choose a centralized approach, where logs from many projects and environments are aggregated into a single logging location. This provides a single pane of glass and simplifies monitoring, alerting, and investigations. However, centralized logging may not always be possible due to data residency or compliance requirements. In those cases, a more distributed approach can be used, where sensitive data remains in specific regions or projects, while operational logs are handled separately. The key is to design an architecture that balances visibility, compliance, and operational simplicity. Another crucial consideration is data residency. Logs often contain sensitive information, including user identities, IP addresses, and access details. Regulations may require that this data stays within specific geographic regions. A good logging strategy takes these requirements into account by carefully choosing where logs are stored and by using log exports to route data to compliant destinations without breaking visibility or control. Granularity and retention are also central to effective logging. Granularity refers to how detailed your logs are. Highly detailed logs can be extremely useful during investigations, but they can also generate large volumes of data, making analysis harder and increasing costs. On the other hand, logs that are too coarse may not provide enough information to understand what happened during an incident. Retention defines how long logs are kept. Compliance requirements often dictate minimum retention periods, while cost considerations may limit how long data can realistically be stored. A thoughtful balance between detail and duration is essential. Access control plays a vital role in protecting logs. Logs are evidence, and evidence must be protected. Only authorized individuals and systems should be able to view or modify log data. This is typically achieved using fine-grained identity and access management controls and by following the principle of least privilege. Limiting access reduces the attack surface and helps preserve the integrity and confidentiality of your logging data. Alerting is another important part of the strategy. Logs are most valuable when they trigger timely action. Well-designed alerts notify the right people when specific conditions occur, such as suspicious access attempts or configuration changes. At the same time, alerts must be carefully tuned. Too many alerts lead to fatigue, which increases the risk that real incidents will be ignored. Cost awareness should never be an afterthought. Logging can become expensive if volumes are high and retention is long. An effective strategy continuously evaluates cost versus value. Techniques such as filtering, sampling, and exporting logs to analytics platforms can help reduce costs while preserving security and operational insight. Finally, a logging strategy is not something you design once and forget. Cloud environments evolve, workloads change, and compliance requirements grow over time. Regular testing, review, and iteration are essential. By validating that logs capture the right information and adjusting the strategy as the environment changes, you ensure that logging remains a reliable foundation for security operations, accountability, and trust. Logging, monitoring, responding, and remediating security incidents in any modern cloud environment. Security is not a single action. It is an ongoing cycle of visibility, awareness, response, and recovery. Logging, monitoring, responding, and remediating security incidents are the pillars that allow an organization to understand what is happening inside its systems and act before small issues turn into major breaches. Everything begins with logging. Logs are the recorded memory of your cloud environment. Every access request, configuration change, network connection, and system action leaves behind a trace. Without logs, security teams are blind. With logs, they can reconstruct events, understand intent, and identify misuse. In Google Cloud, logging brings together data from identity services, compute resources, networks, storage, and applications into a centralized place. This centralization is critical. It ensures that no matter where an event occurs, it can be reviewed, correlated, and investigated later. Logs are not just for after an incident happens. They are the foundation for real-time awareness and long-term accountability. Once logs are collected, monitoring gives them meaning. Monitoring is the process of continuously observing logs and metrics to detect unusual behavior. Normal systems have predictable patterns. Users log in during certain hours. Services communicate in known ways. Resource usage follows expected trends. Monitoring tools learn these patterns and watch for deviations. A sudden spike in failed login attempts, an unexpected permission change, or traffic flowing to an unknown destination can all indicate a security problem. Monitoring turns raw data into signals. It allows security teams to move from reacting after damage is done to detecting issues as they emerge. Detection builds on monitoring by adding intelligence and context. Detection systems analyze events and determine whether they represent real threats. Not every anomaly is an attack, but every attack leaves anomalies behind. Detection rules, policies, and threat intelligence help separate harmless noise from dangerous activity. In Google Cloud, security detection can be based on identity behavior, network activity, API usage, and resource configuration changes. When detection works correctly, it raises alerts that are timely, actionable, and accurate. This reduces alert fatigue and allows teams to focus on what truly matters. When a security incident is detected, response becomes critical. Response is about speed, clarity, and containment. The goal is to limit damage, protect data, and stop the threat from spreading. A strong response process is planned in advance. It defines who is responsible, what actions are allowed, and how decisions are made under pressure. In the cloud, response actions can include disabling compromised accounts, revoking credentials, isolating affected resources, or blocking malicious network traffic. Automation plays a key role here. Automated responses reduce human delay and ensure consistent action during stressful situations. Responding effectively also requires visibility. Security teams must understand what happened, how it happened, and what systems are affected. Logs and monitoring data provide this insight. Without them, response efforts are based on assumptions. With them, decisions are informed and precise. Communication is also part of response. Stakeholders need to be informed, timelines established, and actions documented. A calm, structured response prevents confusion and reduces the risk of making the situation worse. After the immediate threat is contained, remediation begins. Remediation is about fixing root causes and preventing recurrence. It is not enough to stop the attack. The weakness that allowed it must be addressed. This might involve tightening IAM permissions, correcting misconfigurations, patching vulnerable software, or improving network segmentation. Remediation often reveals gaps in security design or operational practices. These lessons are valuable. They help strengthen the system over time. Remediation also includes improving detection and response capabilities. If an incident was not detected quickly, monitoring rules may need adjustment. If response actions were slow or unclear, automation and playbooks may need refinement. Each incident becomes a learning opportunity. Over time, this continuous improvement reduces risk and increases resilience. Logging, monitoring, responding, and remediating are not isolated activities. They form a continuous security lifecycle. Logs feed monitoring. Monitoring enables detection. Detection triggers response. Response leads to remediation. Remediation improves logging and monitoring. When this cycle is well-designed and consistently applied, organizations gain confidence in their ability to protect cloud environments. In the end, security incidents are not a question of if, but when. What defines a secure organization is not the absence of incidents, but the ability to detect them early, respond decisively, and recover intelligently. In the cloud, visibility is power, preparation is protection, and continuous improvement is the strongest defense. Configuring and monitoring Security Command Center. Security Command Center is the place where everything you log, monitor, and detect across Google Cloud finally comes together. Think of it as the central security control room for your entire cloud environment, designed to give you visibility, context, and actionable insight instead of scattered alerts and disconnected signals. Before Security Command Center can protect anything, it needs to be activated. This activation can happen at the organization level or at the individual project level. When enabled at the organization level, all folders and projects underneath automatically inherit its protection, which is the recommended approach for large or growing environments. Once active, Security Command Center begins collecting data from multiple built-in security services and correlating that information into findings. Security Command Center operates using service tiers. The standard tier provides basic visibility into high-severity risks and common misconfigurations, giving organizations a starting point for security monitoring. The premium tier goes much further. It unlocks advanced detection capabilities, full security health analytics coverage, custom detectors, attack path analysis, and deeper threat intelligence. The tier you choose directly affects what types of risks you can detect and how much automation you can apply. At the core of Security Command Center are built-in services. These services continuously observe your environment and look for different categories of risk. Some focus on configuration issues, others on vulnerabilities, and others on active threats. When one of these services identifies a problem, it generates a finding. A finding is a structured security signal that explains what was detected, which resource is affected, why it matters, and how it can be fixed. One of the most important built-in services is Security Health Analytics. This service looks for vulnerabilities and misconfigurations that weaken your security posture. It checks whether resources follow Google-recommended best practices and industry standards. Examples include publicly exposed storage buckets, overly permissive firewall rules, disabled encryption settings, or weak database credentials. These checks are performed either in real time when a resource changes or in batch mode through daily scans. Detectors are the engines behind these findings. Each detector is responsible for identifying a specific type of issue. Detectors run continuously and are regularly updated with new security intelligence so they can identify emerging risks at cloud scale. Some detectors are enabled by default, while others must be explicitly turned on, depending on your organization's needs and cost considerations. Security Command Center also supports threat detection services that look beyond configuration problems. These services analyze logs and activity patterns to identify suspicious behavior, such as compromised virtual machines, malicious container activity, or abnormal access patterns. Instead of relying on a single signal, they combine multiple data sources to reduce false positives and surface meaningful threats. One of the most powerful capabilities of Security Command Center, available in the premium tier, is the ability to create custom detectors. Built-in detectors cover common scenarios, but every organization has unique security requirements. Custom detectors allow you to define your own rules using configuration data, policies, and logic that reflect how your environment should behave. These detectors can identify misconfigurations or violations that are specific to your business. Custom detectors can do more than just report problems. They can also trigger automated remediation actions. This means that when an unsafe configuration is detected, Security Command Center can automatically correct it. For example, if a storage bucket becomes publicly accessible, a custom detector can immediately remove public access. This approach turns security monitoring into a self-healing system that reduces response time and limits damage. All findings generated by Security Command Center are centralized in a single interface, making it easier for security teams to prioritize risks. Findings include severity levels, affected assets, timestamps, and recommended actions. Over time, this allows teams to identify trends, recurring weaknesses, and systemic issues rather than reacting to isolated incidents. Security Command Center integrates deeply with logging and monitoring. Logs from cloud logging provide the raw evidence of what happened, while Security Command Center adds intelligence and context. This combination supports non-repudiation by creating a clear, auditable trail of actions, showing who did what, when it happened, and which resources were involved. Monitoring Security Command Center is not a one-time task. It requires continuous review and tuning. Detectors should be enabled or disabled based on relevance. Findings should be triaged and resolved. Custom detectors should evolve as the environment changes. Over time, This process transforms Security Command Center from a passive dashboard into an active part of daily security operations. In practice, Security Command Center becomes the foundation for detection and response in Google Cloud. It consolidates security signals, reduces noise, highlights real risk, and enables faster, more confident decision-making. When configured and monitored properly, it shifts security from reactive firefighting to proactive protection, helping organizations stay ahead of threats instead of chasing them after damage has already been done. Summary Part 5 focuses on how to run and scale security operations effectively in Google Cloud. Instead of just designing secure systems, this chapter explains how to continuously detect, monitor, respond to, and remediate security issues in real-world environments. The chapter begins by emphasizing that security must be automated. Manual security checks do not scale, so Google Cloud provides tools to automate vulnerability scanning, policy enforcement, and configuration validation across infrastructure, applications, virtual machines, and containers. This automation ensures that security controls remain consistent even as environments grow and change rapidly. A major part of the chapter explains how to secure software supply chains. It covers scanning container images and VM images for vulnerabilities, enforcing trusted images, and using binary authorization to ensure that only approved and verified workloads are deployed. This helps prevent vulnerable or tampered code from running in production. The chapter then moves into policy and drift detection at scale. It explains how organization policies are used to prevent misconfigurations from happening in the first place, while detection tools identify configuration drift after resources are deployed. Together, these approaches enforce security guardrails and restore systems to a safe state when changes occur. A significant section is dedicated to logging, monitoring, and detection, which form the foundation of security operations. The chapter explains cloud logging and cloud monitoring, showing how logs act as security evidence that answers who did what, when, and where. It highlights the importance of designing an effective logging strategy, controlling access to logs, retaining logs securely, and exporting logs to external security systems when needed. The chapter culminates with Security Command Center, Google Cloud's centralized security management platform. Security Command Center brings together findings from multiple security services, detects vulnerabilities, misconfigurations, and threats, and provides a single view of security posture across projects and organizations. It introduces built-in detectors, service tiers, and the ability to create custom detectors that can even perform automated remediation. Overall, Part 5 teaches that strong cloud security is not static. It is an ongoing operational process that relies on automation, visibility, continuous monitoring, and intelligent response. By the end of the chapter, the reader understands how Google Cloud enables proactive, scalable, and resilient security operations rather than reactive manual security practices.